Hey, welcome guys. Yeah, so this is the analysis video, and we talk about differentiation. Yeah, so most of the parts will follow the advanced analysis. So introduction to analysis of the routine, chapter 5. Talking about differentiation and also add some apostle thing. Okay, so this we just finished the configuration. I think differentiation is very easy once you know the once you know the continue the first part. Hope you guys subscribe to my channel. So definition, f is a real value, right? So let's say f is defined on a closed interval from R, and for any x belongs to AB, let's define a quotient. Let's define a phi of t, which is f of t minus f of x, t minus x, and this is only defined, let's say, so let's define this, right? So t cannot be x, and the t is from A to B. And the define so-called f prime of x is just limit t goes to x, phi of t. Okay, so since in the continuous part we know what's limit, so well defined. Okay, if it's well defined, it's okay. So if the limit exists, then we just say that f of x is differentiable. So f is differentiable at x. Okay. Okay, so that's it. Okay, more generally, yeah, so there's a subtlety here that if you only working about A, right, at A or B, right? So if you're working on the A, then you can only approach this limit from right. If you're working on a B, then you can only approach this limit from left. Okay. Yeah, so hopefully, so you can define, it's just why we define the so-called right-hand limit and the left-hand limit. So yeah, so you can define a left-hand limit and the right-hand limit derivative for A and B. Okay, but most of the time that we only care about the interval, which is falls into this region. Okay. Okay, so there's a thing that if there's a remark that if f is defined on A, B, then we cannot talk about whether it's differentiable on A or B. For this closed interval case that one can define it if you just say clearly that you only go from right or you only go from left. Okay. Okay, so theorem, simple. This theorem just say that if f is defined, so f is still a b into r. This is the most of case because remember this is compact set. Okay, as we prove it. So a b then f is f is differentiable at point. So f is differentiable at point x. At the x belongs to AB. So now I use the right hand and left hand limits for A and B. Okay. Then f is continuous. So differentiable implies continuous. Okay, I think this is I think everybody know how to prove, right? So you in order to prove that something is continuous, and you are trying to prove what? You're trying to prove that f of t approach to f of x as t belongs close to x, right? So this is just right. Oh. Sorry, because this is in its previous page. Yeah, so f of t, f of x, right, can be written as t minus x, f of t minus f of x, t minus x, right? And then if you go to, so if t approach to x, and this right hand side become phi of prime of x, t minus x. But this is this means this guy just a finite number, so you approach to 0, right? So you prove that f of t become approach to f of x as t choose x, t goes to x. Okay, because this guy exists and this guy is 0. Okay, so the next is that the differentiable rule. Okay, so let me just quickly say. Okay, so this should be the high school, right? So you know that the f plus g derivative will be f prime minus plus g prime minus, and fg prime is f prime g. Fg prime, this is called Leibniz rule, and you can easily prove this. Okay. Okay, so this is trivial from the limit, right? Because we know that limit is x goes a f plus g is just a sum of it that we already proved. You can use a series to prove or sequence. Okay, also and at least one you can, if you apply yeah, basically you should prove these two. Okay, so let's prove it. So the first one is clear, right? So this one is trivial. So let's prove the second. Okay, so let's define h to be f of g, f times g, and easy to prove that. So h of t minus h of x will be f of t, g of t minus g of x plus g of x, f of t minus f of x. Okay, so hopefully you can see this. So this term cancel. Okay. Okay, so my assumption is that at that point f prime and g prime exist, right? So right. So let's divide it this t minus x. So I can get the f of t times t minus x, t minus x, g of t minus g of x plus g of x, f of t minus f of x, t minus x. Okay, so as t goes to approach to x, then this is guy I don't know what it become, right? So I evaluate the right hand side. So f is continuous because my assumption is that f is differentiable on t equals x. So this is f of x, and then this guy will be g prime of x. Okay, so also this guy is g. This guy is g of x, right? So g of x, and then this guy will be f prime of x. Okay, so finish the simple proof. Okay, so how about the how about f over g? How about c? Okay, so how about c? So how about f divided by g? Okay, so I want to skip this. So basically we will prove because you can write as this, right? So you will need, you can prove this. You get this, right? And this need to use a chain rule. So after we prove chain rule, then it's just very easy. Okay, so once you get this, then you plug it. Yeah, so we can prove C after we prove chain rule. So chain rule is the key. Okay, so theorem, which in the calculus that people don't really give the formal proof. But in this video, we need to give a formal proof. So chain rule. Okay, so suppose I guess everyone knows about it, right? So if f of t eat with g of t, and you do a derivative respect to t, then you get this. Right, so in the calculus terminology, then some smart guy will tell you something which is wrong. You might read that, oh, because dh, maybe you call it h, so dh dt is basically, you can write maybe dh. Let's define h to be g composite with f. Right, so dh divided dt, and we'll approach dh df, right, and df dt. Right, so once you do this, then df over dh over df is viewed as just g prime, right? G prime plug f of x, f of t, right? And the df dt will be f prime of t. So this is the usual hand waving proof, right? But this proof is not so rigorous. So it's not rigorous. So we give the rigorous proof. Don't worry, it's a little bit long. Okay. So let's so and you need to write down the assumption, right? So you need to assume that, okay, so that's first is that the first sort of assumption we need to start is that the f is continuous on AB. So f is let me just write it C0 AB means that it's continuous at AB, and f prime of x exists at x belongs to AB. Some point x belongs to AB. And then there's a g where g defined on the interval I, which contains a range of f. So I should say that g defined on image f, right? Because we will do g circle f, right? So g should define on the image of f. Okay, so g is well defined image of f, and the g is differentiable G differential on what? On f of x, right? Then if you define h of t to be f g t, right? Let's say t belongs to a b, then we have h prime of x, g f prime. So this is g prime, you plug f of x, and then f prime of x. Okay, so this is the detail of the chain rule. So let's give a proof. Okay, so let's say y is f of x, and then we have what? We have f of t minus f of x, right? This is the definition of the derivative. So derivative is this on x, right? So I can remember t minus x, and the f of prime of x, let's say plus u of t. Okay, so this u of t will goes to 0, right? As t goes to x. Okay, and then you still have g of s, let's say g of y equals to s minus y, g prime of y plus v of s, right? So the same thing is v of s approach to 0 as s approach to y, right? So yeah, and let's say, so this s can be arbitrary, right? So these two s can be arbitrary, so that s to be let's be what? F of t, right? So that's f of t. So we got the h of t. So h of t is what? H of t is a g circle f, right? So this is h minus h of y. Let's say the not so right. So you plug y is this, right? So and h is defined to be g circle f. So h of t minus h of x is a g f of t minus g f of x. Okay, and then this guy is just write down all your beautiful definition. What's your g circle? Yeah, this is just left hand side, right? So this is s minus y. So s minus y. So s is f of t minus f of x times g prime of y plus v of s. So this is g prime of f of t. Y is f of x, right? Okay. So now we get this. Okay, so let's divide it t minus x, right? So I get h of t minus h of x, t minus x. So right hand side equals to f of x, t minus f of x, t minus x times these guys, g prime f of x plus v of s. So this is v of, so s is f of t, right? Okay, so now t approach to x. So f is continuous. When t approach to x, then v approach to, so f of t, right? F of t approach to f of x, right? And then you know that the s approach to f of x, then v of x 0, right? So these guys go to hell, right? So you get left hand side is h prime of t equals to f prime, right? This is f prime of x times g prime f of x. This is x, okay? As t goes to x. Okay, so this is the definition, the rigorous proof of chain rule. Okay, so hopefully this is better than your calculus. Okay, very interesting. Okay, so 2 examples. I'll quickly say. This example is not very trivial, so let me just quickly say. So let's define f of x to be x sine 1 over x if x is non-zero, 0 and 0, right? So easy proof that f prime of just sine of 1 over x and 1 over x cosine 1 over x, right? So easy to see that if you let x approach to 0, then this blows up. This is sine infinity, right? So this limit to this limit to this. Okay, but you can prove and right? So f of 0 does not exist. Okay, this so or you just start from the definition, right? You can start f of t minus f of 0, t minus 0. So this is sine 1 over t, right? So this also do not exist. Okay, but if you change f of x to be x squared sine 1 over x, x is non-zero. This is 0, x is 0. This is x is non-zero. And then you write down if you write down the derivative, right? If you write down f of prime of x, you get 2x sine 1 over x minus cosine 1 over x, right? So it seems like that if you go x equals 0, then this image still looks not correct, right? Because these two are not well defined. But you can do the definition, right? So if you write down a definition, and you get f of t minus t, right? So you get a t1 over t, right? And then you can use, but you can bound this by t, right? So by a squeeze theorem, you know that the t goes to 0, and this guy goes to 0, and this guy also bounded by this, right? So from this, you prove that f prime of 0 is 0, right? Yeah. So now, this is why this now you see that why these f prime do not coincident, right? Because f is, so from here we know that f is, so by definition, right? F is if x approaches to 0, this guy also approaches to 0. So you see f is continuous. And then not only continuous, but differentiable everywhere. But f prime is not continuous at x equals 0. Okay, so sometimes you cannot just do the derivative and approach x equals 0. The reason is that this f prime is not a continuous function. So if you just do f prime, then it's fine for x is non-zero. It looks like this, but the x approaches 0. This is not correct. But if you use a definition and you squeeze theorem, then you can prove that the f prime 0 is just 1. Okay, so sorry, f prime 0 is just 0, right? Because this is bounded by t, by squeeze theorem. Okay, so this tells you that in general, you cannot, in order to solve this type of problem, you cannot just do the f prime and try to approximate x to go to 0, because f prime need not to be continuous. So this is the good example. Okay. So from here, the previous theorem, you know the fact that if f is undifferentiable, that means it can at least up to differentiable to n times, right? Then the f previous n minus 1 should be continuous, right? By our previous theorem. So actually, you can define some notation called C of n, or a function a b, which is all I think it's all a function from a to b. And f is let's say f, and f is let's say undifferentiable. And that differentiable should be, I think it should be continuous, I think. So the f of c of 0 will be just a continuous function. A continuous function on AP. If you learn about set theory, you can think about how many continuous functions on AP. Okay. So I will not talk this. Okay, and then you can go define C1 AB. Basically, it's f, and I think f and prime need to be both continuous. And then you can define C2, and then you can define so-called C infinity. Basically, you can infinite differentiable. So for example, exponential x, sine x, cosine x. So everything you know, obviously, most of them should be infinite differentiable. Ooh. Okay, so next, we can talk about mean value theorem. I think once we prove with mean value theorem, then this derivative part should be simple. So let's see the proof. Oh, I think it's not very long. So let's prove it. Yeah. Okay, so this is the mean value theorem. Okay, so let's define. In order to start the theorem, we need to define so-called local maximum. Okay, so f is local maximum. So starting still the old school, AB close interval to R. So if local f is local maximum, that means there exists let's say local maximum on x, means that f of x. Sorry, let's write down. So f is local maximum at x, means that what? Let's say there exists a delta such that when x plus less when t belongs to x minus delta and x plus delta, f of t is less or equal to f of x, right? So local maximum means that at this point x, right, you are greater, right? So there exists a small delta such that in this region that x is the largest one. Okay, now you can define a local minimum, so it's the same by f of t greater or equal to f of x. Okay, so there exists the delta greater than 0 such that this success. Okay, so theorem f defined to be AB, still the old school, so OB to R. And if you have you have a local, suppose you have local maximum or minimum at x belongs to the open interval, right? Because I want to deal with the two sides. Then f prime of x is 0. Okay, so this is almost trivial, right? Because if it's local, let's prove it for local maximum. By definition, you will consider phi of t, f of t minus f of x, t minus x, right? And by definition, right, if it's local maximum, that means if t greater than x, then phi of t minus phi of x is less than 0, right? So if you approach t to the right, if you approach t to the from right, right, you get your phi. So now your phi of t will be what? Will be so t minus x greater than 0, right? But this is less than 0, so you get this, right? So you can easily show that this will imply that phi prime of x. So you need to assume that, okay, so I didn't write down. So f is is differentiable. So I say f is differentiable at x, right? So the condition is that f is differentiable at x, right? Otherwise, that this may not be exist. So if t approaches x to the right, then phi prime of x will less or equal to 0, right? If t goes to x left, then t minus x will minus, right? But this is still minus, so phi prime of x will greater or equal to 0. Right, so you show that phi of x, you showed sorry, not f, sorry. And so you get f prime of x is 0, right? Because it cannot be, if it's greater or equal to 0 or less or equal to 0, then it must be 0. So let's just write it, make it clearly. Oh, I cannot cancel this. Why? What is going on? Oh, okay, don't worry. Okay, so let's talk about the mean value theorem. Okay. So now we go to the proof, MVP. So let's say f and g are continuous, are both continuous. Defined on AB to a real number. So this is the first condition. And the second condition is that f and g are differentiable on open interval. Right, this is some setting. And then there exists a point x belongs to AB such that f of b minus f of a, g prime of x is the same as g of b, g of a, prime of x. Okay, so old school problem. Then this is the theorem called the mean value theorem. So proof. Let's see, proof. So let's define h of t, right? So it seems like I just define h of t to be fb minus fa and a g prime of t, right? So and it minus gb of minus g and f prime, right? So f of b, f of a, g of t minus g of b, g of a, f of t, right? So definition, and the t belongs to ab. Okay. Now we say that h is continuous, right? Right? Why? Because these constant, these are continuous, right? So two composite of two sum of continuous, and h is also differentiable. Okay, and let's say h of a is what? Simply prove your h of a will be f of b minus f of a, g of a minus g of b, g of a, h f of a. Okay, so you get f of b, g of a minus f of b, g of b, right? And you also get the same as h of b. Okay, so this is you need to check. Okay. So in order to prove, so that's the final thing that we need to prove. We need to prove there exists x belongs to the open interval such that f of x, so such that g of prime of x is 0. Okay, and this is the famous Rawls theorem. Okay, and the reason is that so now it's very easy that let's quickly prove the Rawls theorem, right? So now you have h, which is a continuous and differentiable on AB, right? Suppose so now you get this, right? So the first case is h is a constant, right? So if h is constant, then it's fine, right? You don't need to prove anything because h prime is 0, right? For any point x belongs to AB. Okay, so suppose h is not constant, right? Then it must have the local maximum or local minimum, right? Because the reason is what? The reason is what? Okay, so let me tell you. The reason is that the h is continuous on AB. And AB is what? AB is compact. So continuous function on compact set must have the minimum and must have the minimum, local global minimum and local and the global minimum and global maximum, because h is a continuous function defined on the compact set. So there must be some point which is a global, right? So global minimum or global maximum is definitely local maximum or local maximum. So from this, you just easily, from previous theorem, you just easily say that there is this x in AB such that f prime of x is 0, right? So if this is the case, that you just do a derivative, right, and then put x in, then you prove this theorem. Okay, yeah, simple proof. Okay, so final theorem, which is a special case. People usually do it. So if f is a continuous on AB, closed interval AB, so conti, and then f is a closed, f is differentiable on a small interval AB, then there is this x belongs to AB such that fb minus fa is f prime of x b minus a. So this is the usual definition, a usual theorem for MVP. And the previous one are generalization. So proof. Proof simple, just that g of x to be x. And you prove it. Okay. That g of x equals to x and plug in the previous theorem. Okay. Okay. So another theorem, which is that if f is differentiable on AB, then the following three. If f prime of x is greater or equal to 0 for all x belongs to AB, then f is increasing. And f prime of x is less than or equal to 0 for all x belongs to AB, then f is decreasing. And if f prime of x is 0 for all x belongs to AB, f is just constant. Okay, all of it's just on AB. Okay. And the reason is that, okay, so proof is just one line, right? You just use so you know f of x minus f of a, there exists c belongs to ax such that ax belongs to ax open interval such that f prime of c is x minus a, right? So if all of the derivative is larger than 0, then this guy is larger than 0. So it's greater or equal to 0. So this is increasing. If this f prime is always negative, then this is less or equal to 0. Okay, if it's constant 0, then means it's constant. Okay, so basically this, I think the only constant, these are trivial, right? But from the mean value theorem. But this actually proves that when derivative is 0, then you always get constant by mean value theorem, which is not obviously correct if you do not know the mean value theorem. If you only know the derivative is 0, then somehow like if you're in a higher dimension, it doesn't seems like that f should be constant. Okay, so next things we can talk about the continuity of a derivative is the small results. See you guys next videos.